This is a video on significant figures. So in a measurement, all of the known digits with certainty plus one final estimated digit are called significant figures. If we look at a length example first, we have an object in the middle and we have two different rulers that we're using to measure it. If you are using ruler A, without question, anyone would say that the length is between 4 and 5. And let's say it's centimeters that we're measuring. So without a doubt, it's 4 point something. Some people might say it's 4.7. Some people might say that's 4.8, 4.6, 4.9. No matter what, though, this last digit that you're putting there is a guess. So I will say 4.7 centimeters. This 4, no one can argue. That's for certain. This 7 is a guess. You always must guess one digit of uncertainty for significant figures. If you look at ruler B, notice ruler B has more markings. It's more precise. If we look at this is your 4.5, 6, 7. This is your 4.8, and that's your 4.9. Any reasonable person would say that's between 4.8 and 4.9. So we know it's 4.8 something. That something is a guess. We could put a 5, a 6, a 7, any digit there we want. But notice here, the two starred numbers are for certain. The 6 is my guess. This number up here has two significant figures. This number has three significant figures. The more significant figures you have, the more precise your number is. Here is a volume example. So on the left, we have a beaker. In the middle, we have a graduated cylinder. And then on the right, we have a burette, all measuring volume. So if we look at the beaker example on the left, it looks like this number here would be a 50, that little line. So without a doubt, we can agree that it's between 40 and 50. So it's 40 something. So maybe you would say it's 46. You cannot argue the 4. That is your estimate. That has two significant figures. If we look at the grad cylinder, this would be your 36 line. This would be your 37 line. We are reading the meniscus. Again, that is the bottom curve. So that is between 36 and 37. So 36 point, I'll say 4. You can't argue those two. That is your guess. Three significant figures. You must guess. And your burette here. Burettes are a little trickier to read. You read them going down. And this looks like it's going by 0.1s. So 20.1, 0.2, 0.3, 0.4, 0.5, all the way to 21. So this volume is between 0.3 and 0.4. So it's 20.3 something. I'll say 0.35. Notice here we have 4 significant figures. Burettes are way more precise than a beaker. That's why we do not use beakers to measure things. We would use mostly graduated cylinders. Now, how do I know that there's 2 significant figures in 3 and 4? It's not because that's how many numbers there are. There are rules that go along with significant figures, and those are what we are going to do now. There are 5 main rules. The first rule is the easiest. Any non-zero number, digits 1 through 9, are significant. So in the first example here, 4.76 meters has 3 significant figures. The 4, the 7, and the 6. Anything non-zero. The next example, all of those digits are significant, so that has 8 sig figs. Significant figures, we just call those sig figs. And the last one, 1,235, it should have a unit with it, let's say grams, has 4 sig figs. So anything that's not a 0 counts. Easiest rule. The tricky part and the next 4 rules concentrate on the zeros. So the second rule here, the first one with the zeros. says zeros appearing between non-zero digits are significant. This is called the sandwich rule. If you have a zero sandwiched between two non-zero digits, that does count. That is significant. So in 40.7 here, the 4 counts because of rule 1. The 7 counts because of rule 1. Notice how this 0 is between two non-zeros. So that 0 also counts. That has 3 sig figs. The next example, does a big sandwich count? It does. So again, from rule 1, the 1 and the 9 count. And you have 2 zeros now between a 1 and 9. So you just have a bigger sandwich. They both count. That has 4 sig figs. The next rule. Zeros appearing in front of all non-zero digits are not significant. So let's look at what that means. Our first example, notice that these 2 zeros are in front of non-zero digits, in front of the 4, the 5, and the 4. They do not count. But because of rule 1, those 3 do count. So they have 3 sig figs. The next one, 0.0004 micrometers. Again, these are all appearing in front of a non-zero. They do not count. Only the 4 counts. That has 1 sig fig. The way I like thinking about this rule is that you only start counting sig figs when you hit a non-zero number. So you only start when you hit something non-zero. So again, if we go back up here, I'm starting all the way to the left. It's not a non-zero. I'm not going to start counting yet. I'm still not going to start counting. Now I'm going to start counting. So I think this is maybe an easier way to think of it than the actual rule itself. So how about a number like that? How many sig figs? Again, I'm not starting to count yet until I hit something non-zero. Now I'm counting. Does that next 0 count? Yes, because of the sandwich rule. That 0 is sandwiched. And of course the 5 counts. So there are 3 sig figs there. The next rule. Zeros at the end of the number and to the right of the decimal point are significant. They count. So 85.00. Notice these zeros are at the end of the number and they're to the right of the decimal point. So counts from rule 1, counts from rule 1, and then from this rule, they count. He has 4. Likewise, the next example, they're at the end, they're to the right, they all count. There are 6. The way I like to think of this rule, kind of like I changed the wording a little bit, the way I like to think of this one is when you start your counting, when you hit your non-zero number, if the number has a decimal point, you cannot stop counting. That's very important. If it has a decimal point, once you start counting, you can't stop counting. So let me give you a different example here. What if we do 0.040000? So we're not going to start counting until we hit a non-zero. So I'm not starting yet. Now I'm starting. Because it has a decimal point, I cannot stop counting. So all of these would count. So that would be 5 sig figs. And the last rule here is very wordy. I'll just show you through an example. If you have a number like this, 2000, no decimal point, that only has one significant figure. Those zeros are just being used as placeholders to tell you what magnitude you are working with, meaning the thousands. But they are not significant. If you do have a decimal point, and in the sciences is the only time you would see this happen, 2000 point, and then notice there's nothing after the point. That decimal point is there just to tell you that those 4 digits are all significant. That decimal point. You would never see that in math class or anything like that, just in the sciences. So that's the difference. And again, what does significant figures mean? It's all the known digits plus a guess. So in this case, this guy would be your guess. In this case, below, this guy would be your guess. So you can just think of what instrument you would have to use to do that. The top example, if you're thinking of that, you could just have a piece of glassware and you have 0 here, and then you have a line here like that, and then you have water here, and all this is water. Well, you have no idea. You know it's between 0 and 5,000. So you don't know if it's 3,000 or 4,000, so you're guessing that too. And then you know it's in the thousands, so that's your placeholder. So that's an example of that. Now there are 2 separate rules for operations. So if you are adding and subtracting, you are looking to the right of the decimal point. If you're adding and subtracting, you're looking to the right of the decimal point. So how I like to think of this, let's take this top example first. I'm going to rewrite it, 25.1 grams plus 2.03 grams. You want to type the whole thing in your calculator first. Type the entire thing in, and I get 27.13 grams. Now worry about your sig figs. So we are looking to the right of the decimal point. So in the first number, notice we only have 1 digit to the right of the decimal point. In the second number, notice we have 2 digits to the right of the decimal point. Our answer aligns with 2 decimal places, 1 decimal place. Our answer needs to align with the fewest digits that we have. So because 1 is the smaller digit, we can only have 1 decimal point to the right. So that 3 tells you to not round up. So our final answer would be 27.1 grams. So addition and subtraction, you look to the right of the decimal point and always go by the fewest. The next example, 5,400 grams plus 365 grams. Again, don't do anything else first. Just type it exactly in your calculator and write down what you get. And I get 5765. Now, notice we're looking to the right of the decimal point. Well, I don't have any digits to the right of the decimal point in either number, right? I have 0 decimal places here. I have 0 decimal places here. So then you just look at which place you rounded to. Meaning, in the first number, notice I rounded here. That is the hundreds place, right? The ones, the tens, the hundreds, the thousands. So the hundreds place, ones, tens, hundreds. So I am limited by the hundreds place. So I have to round this to the hundreds place. This guy. So this 6, 5 and up tells you to round up, would round that 7 up to 5,800. And that would be my answer. So that is addition and subtraction. Multiplication and division, easier, I think. You're just looking at total sig figs now. You don't care about to the right of the decimal point or to the left of the decimal point or any of that. You're just looking at total sig figs. So in this example here, the problem did not copy over. Just give me 1 minute. You would still type it in your calculator exactly how it shows. So the problem here would be 3.05 divided by 8.47. And this is grams, and that's milliliters. So this is a density problem, it looks like. So you would just type that whole thing in your calculator, and you get this super long number, 0.3600094451. You look at each number individually and count the total sig figs. So this guy up here, they're all significant. So he has 3 sig figs. This guy down here, they're all significant. He has 3 sig figs. You go by the lowest number. So since they both have 3, you would just go by 3. But if one had 2 and one had 3, you would go by the 2. But here, since they both have 3, we would round this guy to 3 sig figs. 1, 2, 3. This guy does not tell you to round up, so you just keep it as 0.360. And the next example there should be 170 grams divided by 15 milliliters. And again, you just want to type that whole thing in your calculator, and you get this number here, which is 11.33 repeating. Again, you're counting total sig figs. So this guy has 2 sig figs. This guy also has 2. Again, you go by the least amount, so you would only want 2. This 3 tells you not to round, so that would just be 11 grams per milliliter. If you have multi-step calculations, so you're adding, subtracting, multiplying, dividing, you're doing a bunch of things at once, do your order of operations. Do not round intermediately. Keep every digit, do a one big step in your calculator, and then use your sig figs. So here we are performing the following calculations here. And again, I'm sorry this did not copy over. But the first example will be 56.50 meters times 37.99 meters. I'll go ahead and write all of these down. I think it'd be a good idea to pause the video and try them by yourself before I give you the answers. But when you're doing these, again, you want to get the whole answer in your calculator and then worry about sig figs. For part A, we're multiplying. We're looking at total sig figs. Both numbers have 4, so our answer should have 4 So that'll be your answer for A. For B, we are adding. So we're looking to the right of the decimal point. This guy has 3 to the right, 3 to the right, 2 to the right. So our answer can only have 2 to the right. So it should be 15.21 grams. And lastly, C, we are multiplying and dividing, so we are looking at total sig figs. This guy has 3, he has 2, he has 2, so our answer can only have 2, so we should get 3.2 milliliters. Notice how the grams cancels and we're left with ml.